In the middle of the 20th century, human communication was expanding faster than the infrastructure built to carry it. Cities and continents were being linked together, but maintaining those connections required immense physical labor, with human operators manually patching calls through massive switchboards. Every one of those calls eventually traveled through heavy, subterranean bundles of copper. These metal veins were the primary way to move information over distance, carrying electrical signals from city to city. But copper has a strict physical limit. As electrical current moves through a conductor, electrons inevitably collide with the atomic structure. Those collisions generate heat. That heat is wasted energy. Because of it, electrical signals traveling long distances steadily weaken and pick up noise. To keep a cross-country transmission clear, engineers had to install expensive, power-hungry amplifier stations every few miles to constantly boost the degrading signal. As the world began demanding more data and higher frequencies, driven by the rapid emergence of computers and television networks, the limitations of electrical resistance became impossible to ignore. The physical capacity of copper was approaching a hard ceiling. The alternative to electricity had been sitting in front of humanity for centuries. Visible light had long been used to send messages, but systems like the heliograph or this field lamp required a direct line of sight, and a sudden fog bank could immediately sever the connection. Science eventually revealed exactly what light was capable of. In the 19th century, physicists like James Clerk Maxwell demonstrated that light is an electromagnetic wave. It possesses the exact same inherent ability to carry information as a radio signal, but at incredibly high frequencies. To use light effectively, engineers needed a way to bend it around corners and trap it over long distances. The mechanism for this is a well-understood optical principle, known as total internal reflection. When a light beam hits the boundary of a dense transparent material at a shallow enough angle, it doesn't escape. It bounces back inward, trapped inside the material. The missing technological piece arrived in 1960, when Theodore Maiman demonstrated the first operational laser. He created a pure, highly focused, and coherent beam of light. Suddenly, researchers had a light source precise enough to encode massive amounts of data. Initial attempts focused on beaming these lasers directly through the open air. Those experiments failed quickly. Even a tightly coherent laser beam scatters rapidly when it hits atmospheric turbulence, dust, or rain. Photons could theoretically carry an ocean of data, but to do so reliably, they required a protected physical pipeline. The world needed a way to guide light continuously through solid matter. Attention turned back to glass. At the time, sending a signal through standard glass was entirely impractical. A light beam would degrade to nothing after traveling just a few meters, leading most experts to conclude that long-distance optical communication was a dead end. Then, in 1966, physicist Charles Kao investigated the exact cause of this optical degradation. Kao realized that the severe signal loss was not an inherent flaw in the physical structure of glass itself. The light was actually being absorbed and scattered by microscopic chemical impurities trapped inside the material during the manufacturing process. He published calculations setting a specific target. For optical glass to replace copper nebricks, attenuation, the rate at which the signal weakens, had to drop below 20 decibels per kilometer. Kao's paper reframed the entire discipline. The barrier to the information age was no longer an absolute law of physics. It was a problem of industrial chemistry, dependent on whether manufacturers could synthesize glass of unimaginably high purity. 4 years later, scientists at Corning Incorporated achieved Kao's target. They successfully engineered an optical fiber with losses low enough to make commercial light-speed communication possible. But creating a single, pure strand in a highly controlled laboratory is very different from manufacturing millions of continuous kilometers of resilient physical infrastructure. Mass production begins with constructing massive cylinders called preforms. These are huge, ultra-pure blocks of glass that already contain the exact internal refractive structure required to trap and guide the light. These heavy preforms are loaded into vertical draw towers and heated until the glass softens. As gravity pulls the molten material downward, the thick cylinder stretches, emerging at the bottom as a continuous thread thinner than a human hair. Pulling that thread requires absolute precision. Automated laser systems constantly measure the emerging fiber, adjusting the furnace temperatures in real time to ensure the diameter never varies, while keeping the entire process perfectly sealed from microscopic dust. The backbone of modern communication exists only because engineers figured out how to take one of the most delicate materials on Earth and automate its flawless mass production by the thousands of miles. Even through pristine glass, photons eventually lose energy. Early optical networks relied on electronic repeaters, which meant pulling the light out of the fiber, converting it back into electricity, amplifying it, and firing a new laser down the line. That expensive bottleneck was eliminated in the late 20th century with the invention of optical amplifiers. By introducing rare earth elements like erbium into sections of the fiber, engineers found a way to boost the photons directly, amplifying the light without ever converting it to electricity. Next, researchers broke the capacity limit of the fiber itself. Through wavelength-division multiplexing, a single beam of light could be split into multiple distinct colors. Each color acts as its own independent channel. By shooting different wavelengths down the same microscopic strand, multiple data streams traveled simultaneously without interfering. This single optical engineering trick exponentially multiplied the bandwidth of existing global networks. Infrastructure that previously carried thousands of simultaneous connections could suddenly handle millions, pushing the capacity of a single fiber into trillions of bits per second. To integrate the global economy, engineers still had to conquer the largest physical barrier on the planet, the oceans. Linking continents requires a fleet of specialized maritime vessels, like this cable ship. They slowly spool thousands of kilometers of heavily armored fiber optics directly into the open water. These deep-sea highways sink thousands of meters into the abyss. Down there, the glass threads endure crushing pressure, corrosive salt, and seismic shifting, operating flawlessly for decades in an environment virtually impossible to reach. Today, that subsea infrastructure is the primary reason global cloud computing functions. When data is accessed from a remote server, it is traveling across the ocean floor via light, not bouncing off satellites. The modern financial system relies completely on the latency-free transmission of those photons. International markets, algorithmic trading, and global commerce are all synchronized precisely to the speed of light moving through glass. We interact daily with wireless routers and smartphones, creating the illusion of a network floating freely in the air. But underneath, human civilization remains completely physically tethered to a global web of illuminated thread.